Hello students, it's time to start section 4.7, optimization problems. Yes, optimization problems. These are story problems that use derivatives to find the optimized value. Now, think about the word optimized. What does that mean? Yeah, it means you want to maximize something or maybe you want to minimize something. So you are using your derivatives to find maxes or mins for certain problems. Maybe you want to minimize cost. Maybe you want to maximize an area. Well, that's what we're going to do in this section of 4.7. So the study of finding extreme values have practical applications in many areas of life. It is common to ask for the best procedure, the greatest value, minimum cost, maximum profit, or the shortest path. In this section, we shall use those skills that we have studied in previous sections to solve practical optimization problems. All right, the optimization procedure. So let's take a look at this. This is fairly similar to what we did with related rates in section 3.9, but it's a little bit different because we're not taking the derivative with respect to time anymore. All right, let's fill in all these blanks. First thing, you want to ask yourself, do you understand the problem? Okay, what are the unknowns? What are the given quantities? What are the conditions? Okay, as far as for what is unknown, I'll give you a little hint. A lot of these give you the unknown in the last sentence of the problem. Okay, it'll tell you the conditions, and then the last sentence will say what's going on. Next, draw a bajillion pictures. Don't draw one. One's not going to help you understand the problem. You want to draw a bajillion pictures to help your brain wrap itself around the conditions of the problem. Draw pictures until you see the relationship. Draw pictures until you know what's moving. Okay, until you know what's moving, what's fixed, and what are your related equations. That's 2. 3, choose their variables. Decide which quantity is to be optimized. Also decide, is it a minimum or a maximum? Then choose other variables to represent other quantities in your picture. Next, step 4, you're going to write your optimization equation in terms of the other variables from step 3. Okay, this is where you have created your optimization equation. If the optimization equation has more than one variable, in step 5, we're going to write secondary equations representing the relationship between these variables. We're going to use these secondary equations, much like we did in previous story problems, to pare down the number of variables in our problem. Next, you're going to determine the domain of the problem. And the reason why we want to do the domain is because you have to check the endpoints. Remember, we're looking for an absolute max or min, sometimes on a closed interval. So you're going to look at the domain. You're basically, let's say if you have a square problem or a rectangle problem, you're going to look at the smallest rectangle possible, and you're going to keep growing the problem until you have the largest rectangle possible. But keep in mind, the smallest rectangle possible is a rectangle of width 0. Okay, and then often you're limited by something. Maybe you're limited by perimeter because you only have so much fencing to go around. But typically you have some type of limit, and that is going to be your domain. Last thing, you're going to find your absolute maximum or absolute minimum using the techniques that we've learned in these last 3 sections. Okay, so you're going to do the first derivative test, check for increasing, decreasing, and then you're going to check your endpoints and see where are my maximum and minimum values. Ready to do one? Let's do it. So let's look at a constrained area. You need to fence in a rectangular play zone for children to fit in a right triangular plot with sides measuring 4 meters and 12 meters. What is the maximum play area for this play zone? All right, so this is what we're looking for, the maximum play area. Now this play zone is rectangular, and this rectangular play zone needs to fit inside this triangle. So I've already drawn a triangle. Now let's draw the play zone. So for example, if I draw this play zone here, this is one possibility. I'm going to do some colors. Let's say I think that's too small. I'm going to draw a different play zone. Again, rectangular. And then I think to myself, okay, maybe that's not where I want to put my fences. I'm going to move it to a different area. I'm going to make my rectangular play zone there. Maybe that's where I need to put my fences. And then notice what I'm doing. As I'm drawing this, I'm kind of realizing how these fenced-in areas are created. I'm basically dragging some rando point along this line. So let's figure out, how can I define that? Well, if I've got this triangle and I put it on a coordinate plane, that is not to scale. Let's do it a little bit better. There we go. And if you look at it here and here, you've got a y-intercept of +4 and an x-intercept of +12. If you were to find the equation of the line, because again, imagine I'm just trying to create some fenced-in area, and my moving piece here is this point. As I slide this random point here, I need to know what's the equation of the line, because as I move that point around, I either have, like if I have the point up here high in the triangle, I've got this blue area rectangle for play zone. If I move my point here, I've got the orange area for rectangle, green area, and purple area. So again, we're just imagining this random point on this very specific line. Well, if you use methods from other classes, from previous math classes, of finding the equation of a line that goes through 2 points, specifically 2 intercepts, you will find that the equation for this line is going to be y equals -1/3 x plus 4. All right, now let's consider this play zone. So I'm going to erase all of my play zones but the green one. So imagine this is bouncing along and y is equal to -1/3 x plus 4. And as I drag it around, this is going to be my rectangle. Well, what are the dimensions of that rectangle? So how wide is it? Well, the whole width of the triangle is 12 meters, but the width of this rectangle here, if the rectangle is defined by this point, is going to be the x-coordinate, right? So the width is going to be the x-coordinate. And then the height is going to be the y-coordinate, which, as we know, is equal to negative 1/3 x plus 4. All right, looking at the last sentence, they say, what's the maximum area for this play zone? Well, what's the area of a rectangle? Yeah, it's length times width. However, this is too many variables. So if I look at this particular rectangle, I've got a length of x and a width of y, but still too many variables. So I'm going to replace y with, in parentheses, 1/3 x, negative 1/3 x, plus 4. I don't know why I can't write a 4. Come on, pen. Yeah, third time's the charm. Okay, so we need to maximize area when the area is equal to, I'm going to write it in simplest form, negative 1/3 x squared plus 4x. Okay, let's take the derivative now of both sides. So I'm going to take the derivative with respect to x of both sides. Although everything's moving around, we're not looking for rates here. So I'm going to get a prime is equal to, the 2 is going to come down, negative 2/3 x to the power of 1 plus 4. Now what we're going to do is we're going to look at the critical numbers for this. So finding my critical numbers, because I want to find the max or the min, I'm going to set a prime equal to 0. So I've got negative 2/3 x plus 4 equals 0. Let's subtract 4 from both sides. And then let's multiply both sides by a negative 3/2. When I do that, I'm going to end up with x equals 6. All right, so this is a possible critical number. But I haven't found my endpoints yet, and I need to do that. So let's look at the domain and endpoints. If I were to look at this situation, basically, I want to look at the rectangle with the smallest width and the rectangle with the smallest length. So in other words, I'm looking, if I were to draw this outside of the box, I'm looking for this where I have the smallest value. Actually, it's in terms of x. So I don't want to look at that. So here, this is going to be my largest length, my smallest width. So I've got a y of 0. Of course, the picture's not to scale. I'm just trying to show it very skinny, very teeny tiny. And then the x is that full value of 12. Then I look over here at this one where I've got the largest width that is possible. So y is equal to 4 here. And here I've got the smallest x value, which is 0. So my domain for x is that x is in between 0 and 12. All right, so let's go ahead and figure out the absolute max and min. Since I have the endpoints, I don't have to do a sign test. If I'm worried that my critical number isn't a maximum, you can go ahead and do a sign test, but just plug values in to see what you have, okay? So I'm going to do a sign test over here on the left. And I'm going to do a plug in chug over here on the right. Now the plug and chug is where I just plug it into the actual area formula. So I'm going to plug it into the actual area formula. And for the sign test, remember, sign test, I'm plugging them into the derivative. So I'm plugging it into -2/3 x plus 4. The only value I have to plug into the sign test is my critical number. And my critical number is x equals 6. So I want to plug something before x equals 6, like x equals 5. And something after x equals 6, like x equals 7. And then we'll see what's happening at the actual value of x equals 6. And we're plugging that into a prime. So if I plug 5 in here, I end up with -10/3 plus 4. And that's going to give me a positive, so that means it's increasing. And then with x equals 7, plug in, I have -14/3 plus 4, and that's going to give me a negative number, so that's decreasing. So this is definitely a critical number located at a maximum. However, remember we have endpoints. We have endpoints of 0 and 12. So what I'm going to do is I'm going to look at my original function, and I'm going to plug in the endpoints, and I'm going to plug in my critical number, and I'm going to see who gives me the maximum A value. So plug it into the original. If I plug in 0 into the original A value, I'm going to get 0. If I plug in 12 into the original A value, I am also going to get 0. And if I plug in 6, I'm going to get 12. All right. I found my max, verified it twice. So let's determine the conclusions. So it says, what is the maximum area for this play zone? Again, I come back to that last sentence. And they're not asking me for the dimensions of it. They just want to know the max area. So I am finding a max area of 12 square meters. Okay. If I needed to find the dimensions, I would keep in mind that my x value is 6. And then I could find my y value by plugging 6 into here. Okay. So 6 times -1/3 is going to give me -2. -2 plus 4 is going to give me 12. All right. This is if they wanted the dimensions. Okay, cool, huh? Let's look at another problem. Okay, this one here. I want you to find the point on the graph of y squared equals 2x that is closest to the 0.14. So I've got this graphed for you. So y squared equals 2x, that's graphed. Here's that point of 1,4. Okay. And what I want to know, so just imagine that like this right here, this is my home planet. And I am stuck on an asteroid that has a path of y squared equals 2x. And I can only communicate when I'm close to my home planet. So if I consider some random point along this path, I would say, okay, from here to here, is that going to be my shortest distance? No, because I'm looking for closest, so it's not going to be that line. What about from here to here? Is that one going to be my closest? No. Okay, here to here. No. How about here to here? We see we're getting closer. Here to here. Or is it here to here? Or is it here to here? Well, we're trying to find the closest point. If you want to click on this link here, it will take you to the site where this is, so you can kind of play with it. I don't know if it'll let me click it while I'm on the pen. Let's see. Yeah. Oh, I guess so. Okay, so imagine I have this point here, and what I'm really doing is I'm traveling along this curve, and then I'm trying to figure out when is the point the closest. Okay, so I don't know about you, but I feel like right around here, this is definitely my closest. Ooh, yeah, okay. All right, so how do I represent that as an equation? Well, let's see. So I'm going to draw a little picture of my current situation. And I never draw it as well as what we can see. And Desmos. All right, and what I need to do right now is I need to be the closest, okay, to the 0.14. Well, closest means distance. Do I have a formula for the distance between 2 points? Yeah, I totally do. We have the distance formula, right? So I've got this rando point here of x comma y, and then I've got this very specific point here of 1, 4. So if I want to look at the distance between them, I'm going to use the distance formula. Now remember the distance formula between 2 points, as we learned in previous math classes, is this following formula. However, if we want to take the derivative of this, the square root is going to cause a couple of problems because we're going to have to use chain rule. So what we're actually going to do is we want to minimize d, but we're going to do it by minimizing the radicand. Okay, the radicand is that thing inside the square root. So in other words, we are going to minimize d squared. And just remember, with the distance formula, it's minus inside the parentheses, it's plus between them. So, like many things, we want to do general minus specific. So when we're setting this up, I'm going to have my general x value minus my specific x value, and then I'm going to square it, and add to that my y value minus my specific y value. Okay, so remember, I always want to do general, okay, minus specific, because it's just easier to have those variables first. Okay, now keep in mind that y squared is equal to 2x. Right now I have too many variables. If I wanted to solve this for y, I'd have to figure out the positive or negative, which one's going to use, and I'd have to do multiple things with it, and no thank you. So actually, I'm going to solve this one for x, and then I'll do the substitution with x. So I'm going to get y squared over 2. All right, so let's do some substitution. So instead of writing x here, I'm going to write y squared over 2. minus 1. And then y minus 4 squared. All right, let me tell you a secret. Don't foil, okay? Do not foil. Every time students foil, it is a headache and it doesn't go well. Keep in mind when we take the derivative here, you can use the chain rule. It's going to be a lot easier. Don't foil stuff out. You're making it too difficult if you do that. All right. Don't forget I warned you. Okay. So we are going to take the derivative, in this case, with respect to y. Because the y is what I have left. So here I'm just going to have this d squared prime. Over here I'm going to take the derivative, so I bring the 2 forward. So 2, leave the y squared alone, y squared over 2 minus 1 half, or minus 1 alone. Reduce the power by 1, and then multiply by the derivative of y squared over 2, which is just going to be y. Next, I'm going to add to that the derivative of the second term. So I'm going to bring the 2 down, so 2, and then I've got y minus 4 I leave alone. That becomes a power of 1, and then I'm going to multiply by the inside of y minus 4, and the derivative of that with respect to y is going to be 1. And if I simplify here, what I'm going to end up getting, so I'd multiply the 2 out, multiply the y, and this 2 out in the front, and dot, 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 I end up with y cubed minus 8. And so if I've got this function here for my derivative, I now need to find the critical numbers. Let's do that. So I'm going to find where this derivative is equal to 0. So I have 0 equals y cubed minus 8. Now be careful. I know it's very tempting, and in this case, actually, it will work, but try to get in the habit of solving these for 0 when it's a polynomial by factoring, so that you don't accidentally miss any solutions. So if I were to factor this, this is a difference of cubes. It's going to factor into y minus 2 times y squared plus 2y minus 4. And for a difference of cubes, this second trinomial, that's prime. Okay, so I can't solve it. This is a no solution for being equal to 0. But this one here, y minus 2 equals 0, is solvable, and I end up with y is equal to positive 2. So yay, I found a critical number. Now, because of this problem, notice that there's no domain here. There's no restriction on the domain. This parabola, the sideways parabola, goes on forever and ever, amen. So the domain for this problem is going to be negative infinity to infinity. So there are no endpoints to check. So we just need to do a sign test. All right, let's take a look. Okay, so now that I've found my critical number and I've identified my domain, I'm going to go ahead and do a sign test because I can't plug in the domain because it's negative infinity to infinity. I'm not limited by the sides of a triangle here. Instead, I just have to check the critical number. Okay, so I'm going to plug in something smaller than 2, so like y equals 0. And then I'm going to plug in something larger than 2, so like y equals 3. Okay, if I plug in 0 into my derivative, y cubed minus 8, I get 0 cubed minus 8, which gives me a negative, which means it's decreasing. And if I plug 3 into here, I get 3 cubed minus 8, which is 27 minus 8, which is going to give me a positive number, so this is increasing. So I did find a critical number, and it's a min. So that means at y equals 2 and x equals, because I need to find that out, I have a minimum distance. All right, so if y is equal to 2, and I need to solve that for x, I'm going to see that x equals 2 is my other answer. So that's it. So I've got a minimum distance. And notice that they're not asking me to find the minimum distance. They're just asking me to find the point on the graph that is closest to the 0.14. Let's take a look at another type of graphing problem. So you've got a rectangle is inscribed inside of a parabola, and this parabola is right here, 25 minus x squared, such that one set of vertices is on the x-axis. So I'm just going to draw one right here. So one set of the vertices of the rectangle is on the x-axis, and the other set is above the x-axis and resting on the parabola. And this is a rectangle, so it's going to look like this. What are the dimensions of the largest rectangle that can be inscribed in this way? All right, well, kind of again, imagine that you're in this situation. You want to draw a few pictures. So what I'm going to do is, much like with the other problem, I'm going to pick a point on the graph and I'm going to move it. In fact, specifically, I always pick a point in the first quadrant, because then I don't have to worry about pesky things like signs getting in the way of my math. And so what I'm going to do is I'm going to imagine if I move this point. So let's say like I pick this point in the first quadrant. What type of rectangle would I draw then? Okay, and I can see that that's going to be my new rectangle. So I'm going to do that a couple times. So I'm going to pick a point up here. Let's take a look at that rectangle that gets drawn. Sorry for the non-straight lines. Okay, now I'm going to do kind of opposite. I'm going to pick a point down here. Let's look at this type of rectangle that gets drawn. Okay. Again, imagine they're actual rectangles and not janky rectangles like I'm drawing. All right, and then I'm just going to kind of draw one in the middle. So again, you're imagining that this point is on quadrant 1. And as you scooch that point around the graph, you're going to have all these different types of rectangles. And remember that your goal is to maximize. You're trying to find the largest rectangle inside this parabola. Well, let's consider a couple of things. First of all, you got some rando point here, and it's bopping along the parabola, so some random x, y. And if I write it all in terms of x's, I would say, okay, x is going to stay x, but y, I use my equation, 25 minus x squared. So each point along here can be described in that way. But now look at this point and how it determines the sides of the rectangle. So looking at this rectangle, here to here is x, right? Here's my random point of my x coordinate. So if there to there, here to here is x, then what is here to here going to be? Yeah, it's going to be x plus x, or 2x. And it doesn't matter where you draw your rectangle. If this value from here to here is x, there's symmetry. That value is also x. So here you've got this rectangle with a length of 2x, with a side measure of 2x. Well, let's look at the height of the rectangle. So here, I've got a height of a rectangle. It goes from here to here. And if I look at the coordinates, the height of all of these rectangles are just y. Okay? But we know that y is like saying 25 minus x squared. So when I find this height of y here, I'm going to say that this is a rectangle that has a height of 25 minus x squared. All right, so let's put that together. Here I've got my height of 25 minus x squared. And here I've got my width of 2x. If I'm trying to find the dimensions of the largest rectangle, then what I'm really trying to do is find the dimensions of the largest rectangle that has these side measurements. And area is length times width. So my area formula would be like that. Right, but I don't want to take the derivative like this. I'm going to have to use product rule, and this one would be an easy fix to get rid of product rule. So let's just multiply this out. So I'm going to have 50x minus 2x cubed. And this is a much better one for me to take the derivative of and try to maximize. Alrighty. Speaking of which, let's do it. So it's in terms of x, so I'm going to take the derivative of both sides with respect to x. Over here on the left side, I'm just going to get a prime. I can write it as dA dx if I want to. Over here, I'm going to take the derivative of each piece. The derivative of 50x with respect to x is going to be 50. The derivative of negative 2x cubed is going to be, if I drop the 3 down, negative 6x squared. Okay, now I've taken the derivative. Now I need to find the critical numbers. And that happens when a prime is equal to 0. So I'm going to say 0 equals 50 minus 6x squared. For this one, I'm going to subtract 50 from both sides. And then I'm going to divide by negative 6. I'm going to reduce it, so get rid of that factor of 2. And then I'm going to take the square root of both sides. And when I do that, I'm going to have plus or minus. Now, the square root of 25 is 5. Square root of 3 is not a pretty number, so I'm just going to write it as 3. And that gives me my value for x. Now, keep in mind, I specifically picked a point in quadrant 1. So I'm not going to use the negative. So my critical number is going to be x equals positive 5 over the square root of 3. I do need to consider my domain. There is a limit to the domain, okay, because it's stuck about being inscribed. Remember, I'm moving this point around quadrant 1, so my quadrant, it's basically going to be here to here, if I look at that. So my x value, okay, if I draw a rectangle that's infinitesimally wide, so teeny tiny wide, I've got an x value of 0 is my smallest. And then if I write one that's infinitesimally high, so it has no height, but it has all the width in it, that is when x is equal to 5. So the domain here is going to be as x bounces back and forth from 0 to 5. And again, just remember that you picked x to be in quadrant 1. Okay, so just imagine if x is in quadrant, here's your point, and it's stuck moving around. If you're quadrant 1, here's going to be your smallest x value of 0, and then kind of drag that point down, and your largest x value is going to be where this graph touches the x-axis, and that's at 5. So your domain is 0 to 5. Right, the nice thing about the domain is that you don't have to do a sign test, okay? You can just plug in your endpoints and then plug in your critical number and see who gives you the largest rectangle. Okay, if you want to do a sign test just to make sure that this value here is increasing before and decreasing afterwards, I'm not going to stop you. But I don't have to because I have a domain. So I'm just going to plug and chug. I'm going to save myself a little time. All right, so plug and chug because I have fixed endpoints. And I'm going to plug it into the regular area formula, which is that 50x minus 2x cubed. Remember, I got that there. Okay, so x in A, I have an x value of 0, I have an x value of 5, and I have an x value of 5 square roots of 3. When I plug that in, I get a 0 here for A. When I plug 5 in, I also end up with a 0. If I plug 5 divided by the square root of 3, I'm going to end up with 500 divided by 3 square roots of 3. And remember, I'm just plugging it into this area formula here. Well, this is definitely my maximum value. Okay. All right, so what are the dimensions? Because they're asking us for the dimensions. Remember that this rectangle is 2x by y tall. So what we need to do is go back to the parabola function, and the dimension is 2x. So 2 times the 5 square roots, 5 divided by square root of 3 is going to be 10 divided by the square root of 3. That's my x value. So remember, this was a 2x. And then my y, remember, is 25 minus x squared. So if I plug 10 divided by the square root of 3 into my 25 minus x squared and simplify it, I'm going to get 50/3. Okay, those are dimensions of my largest rectangle. And do yourselves a favor, don't round unless they ask you to. So I'm going to simplify this cost function. I've got 15x plus 10y, where they told me that the enclosed space is going to be 60,000 square meters. So I know that x times y equals 60,000. Well, I don't want this cost function in terms of 2 variables. So I can either solve for x or solve for y and do some replacing. So if I solve this one for x, I can say that x is equal to 60,000 y. 60,000 is already divided by y. If I solve for y, I can see that this thing is going to be 60,000 divided by x. I don't know, tend to like to work in x's, so I'm going to replace the y with x's. So my c function is going to be 15x. I'm going to leave that alone. And then plus 10y is going to give me 600,000. And then divided by x, which is like saying x to the negative 1. So I'm going to write it like that so I could easily take the derivative. So I'm taking the derivative with respect to x. I'm just going to squeeze that in there. Sorry for the lack of room. I'm going to get c prime is equal to, so the derivative of 15x is just going to be 15. The negative is going to come down here, so I'm going to have negative 600,000, and then times x to the negative 2. Okay, so let's find my critical numbers for that. So for critical numbers of c prime equals 0, but notice that I also have x to the negative 2. So this is also going to be when c prime does not exist. All right, so c prime equaling 0, this is when I've got 15 minus the 600,000, x to the negative 2 equals 0. If I subtract 15 from both sides and then divide by 600,000, I'm running out of room on the bottom here. See if I can squeeze that in. I'm going to end up with x to the negative 2 is going to be 1 over 40,000. Now, if I get rid of the negative 2, if I take the reciprocal of both sides, which is totally legal, I end up with x squared is equal to 40,000. And then if I take the square root, I see that x is equal to plus or minus 200, but we're talking about positive values. So x equals 200 is going to be my critical number. If I look at where c prime does not exist, that happens, again, if you look at it, it's this little pesky guy right here. You've got that negative 600,000 divided by x squared. That means that x cannot be 0. Okay, so x equals 0 is going to be a critical number as well. If I consider my domain for this function, interestingly enough, since this is in terms of x, I'm going to look at for x as my smallest. My absolute smallest would be approaching 0, right? But it can't be exactly equal to 0. So my domain so far is going to be between, I'll write it another way, write it in interval notation, from 0 to infinity. Because the skinniest this thing can be is x equals 0. But that won't give me an area of 60,000 square meters. So that's why the 0 is not included. And then the widest it can be, of course, is infinitely many wide. So this is not a really restricted domain. So that means I have to do a sign test with my critical numbers. So although we already know that 0 is not going to work because it's outside of the domain, we're still going to write it in our sign test. Okay, so here's x equals 0. Here's x equals 200. And I'm going to plug values into my c prime. All right. So smaller than 0 is outside the domain, so I don't have to plug that in. Okay, we're just going to leave that alone. In between 0 and 200, I'm just going to pick like a basic number like 1. And greater than 200, I'm going to pick 201. It doesn't matter. You have infinitely many numbers you can pick. So if I plug x equals 1 into my domain function, and remember, into my derivative function, and here's my derivative function, I'm going to get a negative number, which means it's decreasing there. And then when I plug in 201 into my first derivative function, I'm going to get a positive number, which means that it's increasing. So I have a minimum cost. All right. Now they did not ask us for the minimum cost, but let's just go ahead and write it in our conclusions. And we're going to put our conclusions up here at the top. Can I fit it up at the top? Yeah, I think so. Okay, so I'm going to have a minimum cost of, I'm going to plug this into my cost function here. So I've got a minimum cost of $6,000 when the dimensions are 200 meters by 300, that's equal to y, I'm getting too many y's, by y equals 300 meters. And I just use this fact right here. I know that x is 200, so if I want to find y, I am just going to divide the 60,000 by 200, and I get 300. And this is my answer. Okay, just like the last section that we had of story problems, each one is different. Remember the rules. Write a bajillion problems, write a bajillion pictures, draw the pictures moving so you can see the relationship. Get it all into one variable, then take the derivative, then find the critical number, and then look at the domain, and then see whether you have to do a plug and chug or a sign test. Good luck.